This video we're going to talk about one-dimensional steady-state conduction in a plane wall. We'll talk a little bit about how we can use integration of the heat conduction equation in order to solve for the temperature distribution, and we'll introduce the concepts of thermal resistance networks, which allows us to quickly and simply solve for certain parameters. Let's revisit exactly what we mean by a plane wall. As you see in the figure, from the face at x equals 0 to the face at the right-hand side, the temperature decreases from 20 degrees Celsius to 3 degrees Celsius, no matter where you look along the y or the z axis. So the temperature only changes in the x direction. Therefore, we only see a heat flux vector going in the x direction, so we have one-dimensional heat transfer. Examples of things that might be modeled as a plane wall include the walls of a house, a single pane window, or even something like the bottom of a skillet or an iron. Now clearly, if those walls make up the walls of a house, you're going to have some multidimensional effects at the edges of those walls where they join together. But if you're concerned with the big picture of heat transfer through that wall, modeling it as a plane wall is going to be sufficient. So let's take a plane wall where the inside surface is at T1 and the outside surface is at T2. We want to find Q, the rate of heat transfer in the wall. We might choose to solve the differential equation. So since we're modeling this as a plane wall, let's just look at the x direction. We're going to make a few assumptions. Number one, we're modeling the heat transfer through a plane wall such that the heat conduction is one-dimensional. We're also going to model this as steady state. And finally, we're going to assume there's no heat generation within that wall. Since we're supposed to find the heat transfer rate Q, a good place to start is by applying Fourier's law. This will give us things in terms of perhaps watts. Notice the area. If we've been asked to find the flux, the equation would look the same, except we would have divided through by A, the area. We're going to show now that we can use the heat conduction equation and the boundary conditions to solve for dt dx. Since it's assumed to be at steady state, we can get rid of the partial derivative of the temperature with respect to time, which is the only term on the right-hand side. And we can also get rid of the second derivatives with respect to y and z, since we're assuming the heat transfer is one-dimensional, and so no temperature change occurs in those directions, which means this is all we're left with, the second derivative of the temperature with respect to x. Notice I got rid of those partials since the temperature is only a function of x and not x, y, z, and t. You need two boundary conditions for each direction in which the heat transfer is significant in. You have two boundary conditions at x equals 0 and x equals 1. We now need to integrate this function. So let's multiply each side by a dx, and now we can integrate from t1 to t2. Note that we have a second derivative, so I'm just going to rearrange that a little bit. And I know that the integral of a constant, albeit a constant of 0, is just a constant, which we'll term c1. Now we have dt dx, which we know we need to plug things into Fourier's law and get the heat transfer rate, but since we have no idea what c1 is, let's keep going. We'll multiply each side by dx and integrate again. Now we have an expression for t as a function of x. C2 is just the second constant of integration. And now it's time to start plugging in those boundary conditions. First boundary condition is evaluated at x equals 0. And if we plug this into our equation for t of x, we get that c1 is equal to t1, or c2 is equal to t1. Now that we've solved for one of those constants of integration, it's time to plug in the other boundary condition. So we evaluate t as a function of x at x equals L, and we can get the other constant of integration. Now that we've fully solved the temperature profile, we can go back to Fourier's law. Differentiating t of x, we can now solve for Q. So as you can see, if we solve the heat conduction equation, not only were we able to find Q, but we were also able to solve for the equation for the temperature distribution. Now, so this is our Q, but now let's say that there was really no need for us to get the temperature distribution through the wall. Say all we were after was Q. Well, we could use the thermal resistance concept, which we can also call Ohms analogy. Let's rearrange the equation that we got in part A to demonstrate the thermal resistance concept. All I've done here is I've put the temperature change up top and the L over Ka portion at the bottom. Remember Ohm's law from your basic E class? It says that the current is equal to the voltage over the resistance. Well, the voltage is the driving force for the flow of electric current, and we can make a similar statement about the temperature difference being the driving force for heat flow, and that's exactly what we're going to do here. So we have the idea that Q, the heat transfer rate, is analogous to the flowing current, and the temperature difference is analogous to the voltage. We can think about the thermal resistance as resistance to heat flow. So what would cause the heat transfer rate to decrease? A low K value, which would make this denominator within the denominator increase, and thus the thermal resistance. And you can see that increasing the length over the temperature over which the temperature change has to take place would be another source of resistance to flow. So this is our Ohms analogy. Note that we have this subscript COND on the resistance term. This means that it's the conductive thermal resistance. So in Cartesian coordinates, the thermal resistance to conduction is L over Ka. But Ohm's analogy extends to convection as well from a plane wall. So say that we have our plane wall, and at the right-hand side of the wall at x equals 0, it experiences convection. Now, since the heat transfer by conduction is the same all the way through, we know the heat transfer rate at x equals L. So if we do a surface energy balance at x equals L, the Q going in has to be equal to the Q going out. So if we use Ohm's analogy for convection, we need to define a thermal resistance for convection as well. If I use Newton's law of cooling, I could do just that. The real use in Ohm's analogy is that we can build analogies to circuits. Figure 3.2 on the text shows a composite wall with a different convective condition on either side. Each layer of the composite wall has its own thermal conductivity and width, which we're denoting with L. If we look at the bottom of the figure, they've drawn the thermal circuit. Each node represents a temperature at the interface between the surface and the hot or cold fluid, as well as between each of the composite layers. Each of those layers has their own thermal resistance to conduction, and there's also a convective thermal resistance between the fluid temperature and the surface temperature. We could think of those resistances as resistances in series. The analogy still applies. If connected in series, the total resistance is the sum of the resistances. In this case, we have the sum of the 2 convective thermal resistances and the 3 conductive thermal resistances. We do it a little bit differently when we're adding resistances in parallel. So here we have a composite wall, but the layering is a little bit different. You'll notice also that there's insulation on the top and the bottom, so that the heat transfer is still one-dimensional, no heat transfer in the y direction, only in the x direction. Below is a picture of the relevant circuit diagram. The 2 resistances for the material F and G are in parallel. You'll also remember from Basic E how to add those 2 resistances in parallel. So if we wanted to get the total resistance, we add the 2 parallel resistances to get the equivalent resistance, and then add that to the other resistances as if they were in series. So where Ohm's analogy is really useful is if you have 1D steady state heat transfer. And what we'll see in the upcoming videos is that we can extend the concept of thermal resistances to cylindrical and spherical coordinates as well. If you have 1D steady state heat transfer, it's a really useful way to get the heat transfer rate, or one of the temperatures between the interfaces or surfaces, or required temperature or required thickness, or something like that. As you saw, it's a really nice way to simplify the analysis for composite walls or 1D systems with multiple heat transfer mechanisms. It has its limitations though. You can't use it if you don't assume 1D steady state heat transfer, and it's not going to be able to get you a function of T of X. You won't be able to get the heat transfer distribution. So, well, I hope that was helpful. Thank you for watching, and let me know if you have any questions.